Welcome. This is episode 1, so there's nothing to call back to yet. Instead, let me tell you where we're going. Over this whole series, we are going to build our own tiny chat GPT. Not download one, not call an API. Build one from a single number all the way up to a model that finishes your sentences. And every step happens in one tool, PyTorch. So before we write a single line, let's get honest about what PyTorch actually is and why basically the entire field runs on it. Here's the promise made concrete. Imagine a little prompt box, you type once upon a and the machine streams back the rest word by word in gold. That streaming text is the destination. Everything between here and there is just learning, one layer at a time, how that gold text gets generated. We start from one number and we climb. So what is PyTorch? Strip away the hype and it's three things stacked on top of each other. 1. A numbers engine. It holds and crunches arrays of numbers called Tensors fast. 2. An Autograd recorder. It watches the math you do and remembers how to reverse it, which is how models learn. 3. A neural network toolkit. Ready-made layers so you're not building from scratch. Tensors, Autograd, a toolkit, that's the whole thing. And who actually uses this GPT? Llama, Stable Diffusion. The models you've heard of were trained in frameworks exactly like this one. Most of them in PyTorch itself. It's the default in research labs and in industry, which almost never happens at the same time. When the paper and the product agree on a tool, you learn that tool. Here's the thing that makes PyTorch feel good to write. It's defined by run. As your Python executes, line by line, PyTorch draws the math graph live, in step with you. And that very graph is what Autograd will later replay backward. To learn, there's no separate compile the model first phase. The code is the model. You write a multiply, the graph grows a multiply. It feels like normal Python, because it basically is. But I already know NumPy. Why not just use that? Fair. NumPy does the same array math, and honestly the syntax is almost identical. But NumPy is missing exactly two things, and they happen to be the two things training a model needs. It can't run on a GPU, and it can't automatically compute gradients. PyTorch adds precisely those two superpowers and keeps everything else familiar. Let's talk about that GPU point because it's the whole reason this is fast. Picture two lanes. The CPU lane, a few powerful cores great for general work. The GPU or on a Mac MPS lane, thousands of small cores, all doing the same multiply at once. And the beautiful part, it's the same Python file, one dot to device call and your Tensor hops lanes. Same math, thousands of times the throughput. Installing it is genuinely easy with one fork in the road. You pip install or conda install torch, but you pick a build, the CPU only build, or a CUDA build matched to your NVIDIA driver. On a Mac, you take the standard build and you get MPS for free. Then you verify with one line each. Is CUDA available and the MPS check? If they answer, you're done. Zoom out, picture a glass staircase. The bottom step says Tensor. The top step says talking model. Every episode is one step up that staircase. Tensors, then Autograd, then layers, then attention, then a full GPT. Today, we just stand on that first step and make sure it holds weight. Let's run our first Tensor. Here's hellotorch.py, a tidy little program that fits on one screen. It does 5 small things, prints what PyTorch we've got, builds a Tensor, picks the best hardware, does a little math on it, and reports back. Nothing fancy. The goal is just to see real numbers on real hardware with our own eyes. Let me walk it section by section. First, the import and the banner. Import torch, that's the entire library, one name. Then we print the version and we ask 2 questions on one line. Is CUDA available and is MPS available? Those booleans tell us which hardware lane we'll get. On my machine, it'll say CUDA false, MPS true, that's a Mac. On a cloud GPU box, it'd flip. Next, we build the tensor, torch.tensor with 2 rows of 3 numbers, a 2 by 3 grid. The trailing dots, like 1 dot, make them floats, not integers, because all our model math is in floating point. This little grid is the atom of everything we'll build, every weight, every word, every prediction. They're all tensors like this one, just bigger. Now the important part, pick the best device. We check CUDA first, then MPS, then fall back to plain CPU. Whatever wins becomes our device. Then X dot to device physically moves the tensor's numbers onto that hardware. This exact two-step, choose device, then dot to it, is the pattern you'll repeat in every single program from here on. With the tensor on device, we do 2 operations. An element-wise one, multiply every number by 2, which just scales each cell independently, and a matmul, matrix multiplication, between our 2 by 3 and a 3 by 2, which gives a 2 by 2. Element-wise and matmul are the 2 kinds of math that stacked thousands of times become a neural network. That's not an exaggeration, that's the whole game. Finally, we print the receipts, the result shape, its D-type and its device, so we can confirm it really did run on the GPU or MPS and not quietly on the CPU. And we close with our North Star, building toward a model that finishes your sentences. That's the staircase, one step climbed. Next episode, we go all the way down to the bottom step and live there for a while. Tensors, the only data structure that actually matters. See you there.